Hi students, welcome back to the lecture series on Python programming. In our previous lecture, we have seen uh, the number systems introduction, the types of number systems available, and also we have seen uh, the decimal number system and binary number system, and the conversions between a decimal number system and binary number system. Okay, we have designed a few algorithms also. So let us go through the things that we discussed in our previous class quickly. So we have started with a simple introduction to the number systems. We understood that there are four types of number systems available, starting with the decimal number system, then binary number system. The third category is octal number system, and finally, the fourth one is hexadecimal number system. So we understand that every number system has its own base. The decimal number system has base 10. That means the number of digits used in decimal number system is 10. Then binary number system uses base 2. That means the number of digits used in binary number system is 2. Similarly, octal number system uses base 8, which means that the number of digits used in octal number system is 8. And finally, the hexadecimal number system uses base 16, which means that it uses 16 digits, where 0 to 9 are the 10 digits used from decimal number system, and the remaining 6 digits, that is from 10 to 15, are represented by the alphabets A to F. Okay. Then we discussed about how these positional values are used to calculate the actual value represented by a particular number in a particular number system. So we have seen some examples also. And then we discussed about how a binary number can be converted into a decimal number. I have shown you some examples for converting a binary number into decimal number system. Similarly, we have seen an example program for converting the decimal number, a given decimal number, into binary number. And I demonstrated that by executing it through the IDLE. Then we discussed about how to convert decimal numbers into binary numbers. Okay, I have shown this also with the help of examples. Then we discussed about the algorithm for converting a given decimal number into a binary number. Okay. Also, we have demonstrated this by executing it through the IDLE. So up to this part, we have discussed in our previous class. If anybody has not watched this video, the prequel of this particular video, please watch that part 1 of this number systems video first, and then come back to this part 2 of number systems video. Okay. Right. Now let us start our today's lecture. We'll begin with the remaining conversions. So as a whole, what we have is four number systems, that is decimal, binary, octal, and hexadecimal. We have already seen two conversions, that is from decimal to binary, and then binary to decimal. Two conversions we have already seen. These are very important, so we have designed algorithms also. Okay, these two have completed in our previous lecture. Okay. And the remaining possible conversions are going to be decimal to octal. Okay. Similarly, decimal to hexa. Okay. So decimal to octal and hexadecimal numbers. So this is we need to understand now. Similarly, the reverse, octal to decimal and hexadecimal to decimal. So overall, four conversions are required here. Then we will see how to convert the binary numbers into the remaining two. That is binary to octal and binary to hexadecimal. Similarly, from octal to binary and hexadecimal to binary. A total of 8 conversions now we need to understand. And then the mutual conversions between octal number system into hexadecimal number system. So it is how to convert a octal into hexa number system and the vice versa from hexadecimal number system into octal number system. So together we need to learn 10 conversions nearly to understand how the number systems works. Okay, so let us start with the first conversion. That is, we will start with how to convert a decimal number system that is in base 10 into a number in base 8 octal number system. So you can see the process here. Assume that 149 is in a decimal number system. To convert a decimal number system into any number system, you take the target number system's base. So the target number system's base is 8 here. Therefore, you divide the number by 8 and take down the reminders. So 8 divides the number 149 with 18 by giving the remainder 5. And continue the process of dividing by 8 until you get a quotient 0. Okay. So again, 8 twos are 16. The remainder is 2 now. 8 zeros, the remaining number is 2. And then take these digits from bottom to up direction. That means 149 in base 10 is equal to 225 of base 8. So that is how you can convert a decimal number into octal number. So simply remember that if you want to convert a decimal number into any other number system, you just divide the decimal number by the base of the corresponding number system. Okay, so if you are converting it into octal number system, divide the number by 8. If you are converting it into binary number system, then divide it by 2. If you are converting it into hexadecimal number system, then divide it by 16 and so on. It depends on the target number system's base, right? Now let us understand the same example with another one. That is, I just want to convert 58 into octal number system. So assume that 58 is in base 10, that is in decimal number system, and I want to convert this into base 8, that is in octal number system. So what we do, we consider the number and we start dividing this number by octal number system's base is 8, therefore we divide it by 8. So divide the number by 8. So what it is, 8 sevens are 56, and I will write down the remainder 2 here. Again, because the quotient is not 0, we repeat the process again. Divide this number by 8 again. 8 zeros it goes, okay, and the entire number, that is 7, comes over here. Because the quotient is 0, the process is stopped and we will consider the digits from bottom to up direction. Therefore, 58 in base 10 is equal to 72 in base 8. Okay, so that is how you can convert a decimal number into octal number, right? Next, how to convert decimal numbers into hexadecimal numbers. So we know that the base of hexadecimal numbers is 16. Therefore, if you want to convert a decimal number into base 16 number, you have to divide this given number by 16. Okay, so let us consider the first example, 138. It goes like 16 8s, 128. Okay, and the remainder is 10. So what you need to understand is 0 to 9 digits are directly used in hexadecimal number system, and starting with 10, the digits are used with alphabets. Okay, so 10 to 15 are used as alphabets, starting from capital A to 15 is represented by F. Okay, no. So 10 is represented by A, so you have to write it as A. Don't consider this 10. Remainder is 10, which is represented by A, the letter A. Then because quotient is not 0, divide that quotient again by 16. 16 zeros, and this number comes as remainder over here. Okay. Now you take down these values in bottom to up direction, this direction. It is 8 and then A. So you have to write it as 8A. You should not write 810 because 10 is replaced by the symbol capital A. So 138 in decimal number system is equivalent to 8A in hexadecimal number system. Okay. Similarly, I just want to convert another number which is in base 10, 49. I'm considering another example of base 10 is equal to how much in base 16. Okay, let us consider this now. So take down that number 49 and divide it by 16. Okay, because you want to convert the number into hexadecimal, take the base for division. So 16 3s are 48 and the remainder is 1. Okay, because the quotient is not 0, you need to repeat the process again. It goes with 16 zeros and this comes as remainder, that is 3. And the quotient is 0 now. The number is 31. So 49 of base 10 is equivalent to 31 of base 16. So that is how you can calculate the hexadecimal equivalent of a given decimal number. Okay. So I hope you understood that conversion process from decimal to other number systems now. Let us continue with the remaining conversions also. The next conversion is from binary to octal number systems. Okay, so given a binary number, how do you convert that into octal numbers to the base? From base 2 to base 8. It's a simple process. What you need to do is the process goes like this. Take down that binary number and group the bits 3 bits at a time. Okay, 3 bits at a time. You group 3 bits at a time, starting from rightmost bit. Okay, moving towards leftmost bit. Okay, that means if the binary number is suppose this is the example given 1 0 1 0 1 1 0. This is the binary number given there. Okay, so you start at the rightmost bit and group 3 bits like this, and then next 3 bits are grouped like this. And because we have only 1 bit, you can add sufficient number of zeros to make it 3-bit grouping, or else you can take down that 1 bit directly. Now write the decimal equivalents of these 3-bit groupings. So as a shortcut, you can remember these decimal equivalents or octal equivalents of these 3-bit groupings. 000 is represented by 0, 001 is represented by 1, 010, 2, 0113, 1004, 1015, 1106, 111 is 7. Therefore, 110, what is 110? It is 6. So write down that the decimal equivalent here 6. 010 is 2. So write it as 2 here. And then 001 is 1. So this makes it as 126 of base 8. This is how we can convert. It's a simple process. You just need to group from right to left, consider 3 bits, every 3 bits, and write down the decimal equivalents of the 3-bit groupings. Okay, that forms your octal number directly, right? It's a simple process, so I'm not giving another example for this. You can easily understand this. The next thing is conversion of a binary number into hexadecimal number. Okay, so for this you need to remember 4-bit groupings and the equivalent hexadecimal numbers over here. You can remember it. 4 zeros represented by 0, 0001, 1, 0010, 2, 00113, 01004, 01015, 01106, 0111 is 7, 1000 is 8, 1001 is 9, 1010 is A, 1011 is B, 1100 is C, 1101 is D, 1110 is Z, 4 ones is F. Okay, so if you remember these equivalent representations, 4-bit representations of 0 to 15, then you can easily convert any given binary number into hexadecimal number. Okay, so the difference between conversion from binary to octal and binary to hexadecimal is, in binary to octal, we will use 3-bit groupings from right to left, and in conversion into hexadecimal, binary to hexadecimal, we will use 4-bit groupings. Okay, 4-bit groupings from right to left. So that is what you need to remember. It's going to be 4-bit groupings from right to left. Okay. The direction of grouping bits must be from right to left, not from left to right. That means you should start at the least significant bit and move towards the most significant bit of the corresponding number. So let us consider the first example, 101101. Okay, 101101. If necessary, add one more zero here. Any number of zeros can be added towards the most significant digits. It does not matter how many zeros you add. There will be no change in the actual number represented by the binary number. Okay, you should not add zeros towards right side, that is towards least significant digit. That will change the original number. You can add any number of zeros towards left side. Okay, right. So this is the number given. Start from the rightmost bit and group 4 bits. That makes up 1101. Okay, so what is the number represented by 1101? This is 1, this is 2, this is 4, and this is 8. Okay, since this is 0, you cannot consider this 2, and the remaining 8 plus 4 plus 1 makes it up 13, represented by capital D. Okay, similarly here it is 0101, which means this is 1, this is 2, this is 4. So 4 plus 1, because this is 0, 4 plus 1 is 5, and the number represented is 5D in the base 16. Okay, so what is the point here? You need to group 4 bits starting at the rightmost bit. Okay, and write down the equivalent decimal numbers. Another example is given, 11010.10101. There is a decimal point in between, so you need to consider the integer part first and use the process just be used here. Perform a 4-bit groupings here and write down it 1A16 here. Similarly, while considering the binary number after decimal point, you need to perform the 4-bit groupings from left to right. That is what you need to understand. So in octal, you need to perform 3-bit groupings from left to right if you have a decimal point. So like this, from this direction to this direction. Okay. So 10101 is the number. So 10101. After that, because 4-bit grouping is required, add 3 more zeros here. Right. So the first 4 bits represents A, and the remaining 4 bits represents 8. It's going to be A8. So overall, this number is represented as 1A dot A8. 1A is from here, the integer part, and A8 is from the real part, that is decimal part. So you just combine them together with a decimal point. Okay, so if floating point binary numbers are given, then you can convert them into hexadecimal or octal numbers like this. Okay. So let's move on to the next conversion. It is octal numbers into decimal numbers. So how do we convert octal numbers into decimal numbers? This is actually done uh, by using the positional values of the octal numbers. So suppose if you want to convert 67 into a decimal number, then you just write down that octal number over here, and starting from the least significant bit, moving towards the most significant bit, you will start at 8 power 0 as the positional value and move towards 8 power 1, 8 power 2, and so on. Okay. So this makes it as 8 power 0 into 7, the first number, and then 8 power 1 into 6. It's going to be 48 plus 7. That makes us 55 of base 10. So 67 in base 8 is equal to 55 of base 10. Okay. Let us take another example. Suppose I'm considering 53 in base 8. I want to convert this into a decimal number. So how do we convert this? By considering the positional values and then multiplying the positional values with the corresponding digit at that position. Okay, so take down that 53 at this position and this position. We will start with the positional value 8 power 0. Okay, so this is 8 power 0, and then this is going to be 8 power 1. If any other digit is there, it is going to be 8 power 2, and so on. So this is 5 8s, it is 40 plus 3. It's going to be 43 in decimal number system. Okay, so that is how you can convert any given octal number into a decimal number. Okay, just take down that positional numbers and then multiply them with the digits at that particular position. So just remember this point that whenever you want to convert a particular number system into decimal number system, then you require positional values. Positional values are used based on the number system you are using. It depends on the base. Okay, right. Let's move on to the next conversion, which is conversion of octal numbers into the binary numbers. So we earlier we saw that how to convert a binary number into octal number. This time it is octal numbers into binary numbers. It is even simple if you can remember the 3-bit codes of the digits in octal number system. Suppose if you want to convert this 126 into binary number system, then you just take down that bits 1, 2, 6 like this and represent those digits using 3-bit codes. So 1 is 001, okay, and 2 is 010, and 6 is 110. Okay, just write down that and then discard any zeros on right side. You will get the corresponding binary number. Okay, 1010110 like this, right? It's a simple process. There is nothing difficulty in that. The next one is conversion of hexadecimal numbers into decimal numbers. This is also done with the help of the positional values again, but this time the positional value starts with 16 power 0 and moves towards 16 power 1, 16 power 2, and so on based on how many digits are available in that hexadecimal number. Okay, so it is given as 8a to the base 16. So I will write down the digits over here and write down the positional values in the corresponding positions. So this becomes 8 into 16 power 1 plus a into 16 power 0. We know that a is equal to 10, right? So this is going to be 10 into 1 plus 8 into 16. This is going to be 128 plus 10. That gives us 138 of base 10. So it's a simple process to convert any given hexadecimal number into a corresponding decimal number. So let us take down another example here. 149 of base 16 is equal to how much in base 10? It's a simple question. You can try this. Okay, it's going to be a number that is equal to 9 into 16 power 0. We'll start with 16 power 0, right? The positional value. 4 into 16 power 1, that makes it as 64, plus 1 into 16 power 2, that is 256. So 256 plus 64 plus 9. You can calculate that value. It's going to be 256 plus 64 plus 9. What is it? 73, 79, 129, 329. The answer is going to be 329. Okay. Like this, you can convert any given hexadecimal number into a given decimal number like this. The point is, you need to use the positional values for converting a hexadecimal number into decimal number. Okay. And the next thing is, how do you convert hexadecimal numbers into binary numbers? It's an easy process. You just you just have to use 4-bit representations of the digits given in the hexa number. Okay. So it is given as 5D of base 16 here. The 4-bit groupings of 5 is going to be 0101, right? And for 13, it's going to be 1101. Why it is 13? Because it is given as D. D is represented as 13. Okay. So for 13, it's going to be 4-bit representation is going to be 1101, and you can discard any zeros on right side, and the remaining numbers are grouped together to make the binary number equivalent to the hexadecimal number. Okay. So that is how we perform that hexadecimal numbers conversion into binary numbers, a 4-bit grouping simply. Okay. Next, the last conversions that need to be discussed is how do we convert octal numbers into hexadecimal numbers? Then how do we convert hexadecimal numbers into octal numbers? We cannot do this conversion in a single step. Okay, so we need 2 steps to be performed. There are 2 methods for converting octal numbers into hexadecimal numbers. The first method is we know how to convert an octal number into a decimal number. So convert that octal number into decimal number first. Okay, and then convert that decimal number into hexadecimal number. So this is going to be the first method, but not that easy to convert octal numbers into decimal and then decimal numbers into hexadecimal numbers. Okay. And the preferred method for converting octal numbers into hexadecimal numbers is first the octal number is converted into a binary number, because we know how to convert a binary octal number into binary number. Okay, and then use this binary number to convert it into hexadecimal number. In either way, you can get the equivalent hexadecimal number from the octal number. Okay, so this is method 1. Okay, and this is method 2. Method 2 is an easy method because we know how to convert octal numbers into binary numbers with the help of 3-bit representations. Okay, so either method you can use. This is going to be the preferred method. It's easy. Octal numbers are represented as binary numbers using 3-bit representations, and then we can group the 4-bit representations to convert it into hexadecimal numbers. Similarly, conversion of hexadecimal numbers to octal numbers can also be done in a similar fashion. Just reverse that process. We have 2 methods again. Okay, you can start at a hexadecimal number and convert it into a decimal number first, hex to decimal number. Okay, and then from decimal number to octal number. So we know these two processes, right? We know how to convert a hexadecimal number into decimal number, and then we know how to convert a decimal number into octal number also. So you require two steps. This is going to be method 1, and in method 2, what we do is hexadecimal numbers are converted into binary numbers first. Okay, just like in the previous conversion, we convert it into binary number, and then this binary number is converted into octal. So this method is always going to be easy. Okay, so I'm leaving this part of converting octal numbers into hexadecimal numbers as well as hexadecimal numbers into octal numbers to you. Please practice these conversions with some examples. Okay, right. So that's all for today. I think we have covered all the conversions uh, of binary number systems from one that is from one number system into another number system. We have covered all of them. I have shown some examples also. Please practice these conversions with other examples also. Okay. So thank you all for your patient listening. See you in the next lecture. Thank you.